Hello everyone. Today we start off with error calculations. All right. So I'll probably kick off by explaining to you a couple of terms like actual uncertainty and error, percentage error, fractional error. Okay. So let's start off. We say, for example, a simple sample of readings that you get. Say you do that by swinging your pendulum and you're trying to find the period of an oscillation. So you swing the pendulum and then record with a stopwatch. So you get 1.2 seconds, 1.5, 1.7, and 1.8. Okay, based on the instrument that you have, say for example your stopwatch, it gives you a precision of up to 0.1. So you can record up to 0.1 second, all right, in terms of the readings that are displayed here. And hence, because of this, we will say that the actual uncertainty 0.1 second, all right, because it's measured up to 1 decimal point, all right. So what we do is that we take an average reading. So to get an average reading, we'll be using all these to sum it up, and you will end up with 1.55 seconds. Okay. So if the t is used to represent the period, all right, so t will therefore be represented in this manner, which is 1.55. Plus minus actually the error, which is 0.1. Okay. So the key thing to take note in terms of the significant figures and all that, firstly, obviously, this is not correct, because you need to bear in mind that if all your measured readings has 2 SF, 2 significant figure, then whatever calculated readings you have must also have the same minimum number of the significant figure, which is 2 SF. So in this case, it should be 1.6, all right? Hence, in the exam, if you were to represent the reading of your period in terms of 1.55 plus minus 0.1, that will really not be correct. That will be wrong. Okay? So the correct way to represent it is 1.6 plus minus 0.1. You must also take note that the based on the error, all right, if it is displayed to 1 decimal point, then whatever reading that you have must also be displayed to the same decimal point. Okay, yeah. So in conclusions, what we have learned now is that we have noted that actual uncertainty, all right, is actually 0.1 second, and actual uncertainty is always 1 significant figure, by the way. Okay. And the other next 2 calculations we're going to go is to introduce the next 2 terms in terms of measurement of error, which is actually your fractional uncertainty and your percentage uncertainty. So for fractional uncertainty, I think it's quite clear that you'll be taking 0.1 divided by 1.6, so that'll be 1/16, and it's without unit. And this is probably the only time in physics that you will leave your answer as a fraction. The other one is obviously your percentage uncertainty. So percentage uncertainty is 0.1, 1.6 times 100%. Okay. Okay, you end up with 6.25%, and obviously if you write it up again to 1 SFG, 1 significant figure, you'll be 6%. Why 1 significant figure? Because 0.1 is 1 significant figure, okay, and 1.6 is 2 significant figure. So our calculated reading must follow the least significant figure, which means I have to follow the significant figure of 0.1, which is actually 1 SFG. Okay, so that's the final answer. Okay, so that's the first part. The second part that we're going to run through is to tell you the 2 sets of formula that you typically will use for your calculations for exam. Okay, the first set involves addition and subtraction. In the addition and subtraction, all right, you can see that the when you actually compute your error, all right, you just actually simply just replace them. Instead of A, you replace, you change in A. However, you have to keep your whatever dimensionless constant is inside. Okay, so the mathematical proof is here. So if you decide to actually differentiate, all right, by dt, du over dt, then you let that be changed in t, and then you get change in A equal to this. This will actually give you the proof as they will give you the proof as what is given. So the next one is the proof for division and multiplication. So for us, we give a simple example of a equal to 5bc squared. So here is a mathematical proof that you do, all right, for you to show that eventually you end up with change in a over a, change in b over b, plus 2 change in c over c. The key thing is to make sure that if you actually have a certain power, it could be 2/3, could be 1/2, just make sure you bring down the power. All right, if it's minus half, when you bring it down, you still it is still half. All right, you still take the positive value because the error is always to calculate based on the maximum error. All right, so bear in mind that this is a formula that we use for applications. All right, the mathematical proof as dictated down here on the whiteboard is not required. Okay, thank you.